Hello, my name is Henriette. I'm a PhD student in astrophysics at Charles University in Prague and former software developer. In the last part of the series, we designed a program to calculate an n-body problem, and we talked about how to put the input parameters inside of it and about object-oriented programming. Now, in the last part of the series, I want to first spend a little time to talk about comments. Everyone knows that you are supposed to put a lot of comments into your program, but what are the really necessary comments? And while a lot of it is left up to interpretation, there are some rules I can give you. First of all, we talked about how each file in your program has to have a very clear, defined purpose. So it makes sense that at the top of each file, you put a little comment detailing what this file is to be used for. So for example, if I had my configuration file, I might make a comment on the top that says, okay, this file contains all the functions needed to read the configuration file. If you use object-oriented programming, you will typically have no more than one class per file. So instead, you might just use the description string of your class for this. Similarly to classes, each variable you define should have its dedicated comment. So if I, for example, was to define the apocenter and pericenter distance of my cluster, then I should have a comment behind it that tells me that the R-apo is the apocenter of the cluster and R-peri is the pericenter of the cluster. And since we are in physics, don't forget the physical units. The same is true for functions. So functions get multi-line comment strings. In Python, it's below the function header. In languages like C, C++, it would be above. And these strings tell us that, for example, if I have a function that computes the eccentricity of a cluster on its orbit, then I might have a string like this, where the first line is dedicated to a short description of what my function does. So this function computes the eccentricity of the cluster. Then I want to have one line for each input variable. And then I want to have one line for each output variable of the cluster. And of course, always with the physical units. Now, if you need more than one line for the description of your program, you would put it at the end of this block. However, if you notice that you need a long time to describe what your function does, you might think about splitting it up into multiple functions. Okay, so we have written our program, we committed everything, we have it up and running. Now we have to test our program. And the thing about scientific programs is that they grow. So at some point, I will probably want to adjust my program, want to add some new functionality, anything like this. And that means that I would have to retest everything at that point. And testing everything over and over and over and over again takes a lot of time. So is there a way that we don't have to do that? Well, if I ask like this, of course there is. So the way to deal with this is called unit tests, and I brought you a little example to show how unit tests work. So let's say we have, again, a little program. You can see here that in my project folder, I have, as before, the main file and the source file for, in this case, only one subfile. But I also have a test folder. And in this test folder, I usually mirror the folder structure of my source folder. And I put for each file that I have in the source folder a little test file. Also, to make this work, I'm going to use pytest here. We need to have this little init.py file, which typically is an empty file. You could have some definition of structs or whatever you wanted to use in there, but it's usually just an empty file that is needed for Python to be able to run these tests. Okay, let's look inside of these files. So we see our main file here. All the main file does at the moment is to call this compute eccentricity function that I defined in the compute eccentricity file here. And what you can see in this function is that If it goes all the way down here, it will just return the eccentricity based on this equation from the apocenter and the pericenter. However, if we want to use the equation, we need to make sure that our apocenter is always larger than the pericenter. So I included a little test here that deals with this and that will raise an error if this condition is not fulfilled. Now, for those of you who aren't familiar with this kind of error handling, what happens is that if the program comes into this part here and it notices that the pericenter is larger than the apocenter, when it sees this raise keyword here, it will abort the function at this point, and it will raise this value error with this error message here to the next level above it. Next level above it, in this case, is the main function. And you see that here I don't have any error handling yet, which would mean that the error would be handled up even one level further. And in this case, the program would just abort its execution completely and it would print out this error message here and tell us that something was wrong. So let's demonstrate this. And we see that we indeed get an error here. And we get a value error as defined here. And we get the error message that we defined here. We can, if we have this kind of error, also include some error handling. So what does that look like? Well, let me comment in this part again. What you see here is this try except environment, and what's happening here is that the program will just execute this function as normal. However, if it encounters an error, it will not abort the program, but it will move towards the corresponding except branch down here, and it will execute whatever is defined in there. In this case, it will print that an error occurred. So you can see here, it now doesn't crash the entire program, but it just does some error handling that we define. We can also define that we want to have a specific error handled a specific way, and we could even check for a specific error message, which I don't show in this short example. And what you see here is that now the value error has another defined behavior than other kind of error. So if I run it here, it will tell me a value error occurred. And if it finds some other error here, so let's just turn this into maybe an exception, it will go back to the default branch down here. Now, just to turn that. Okay, so this is what our program does for now. Now we want to test this program. And for that, I have this part here for my testing. And let's for now just remove the pytest approx. I'll show you what that does in a second. Okay, so what I like to do if I test this kind of function is I like to test it with known values of astronomical objects. So in this case, I looked at the Earth and I looked at Wikipedia and just copied the values for the apocenter distance, pericenter distance, and eccentricity for Earth. Now, if I have these values, then of course I know, okay, if I enter these values in my function, then I expect this value to come back. So I can just make an assort call where I check whether my compute eccentricity function really equals this part. And if I want to run this test, that's rather easy. I just have to type pytest into my terminal here. And it will run all of the tests it finds in my test folder. Well, in this case, we see here that it says the test failed. And it also tells us that it found out that the result of this equation equals 0.0167114 and so on, while it just expected the value of 0.0167. So you can immediately guess that the accuracy of this is too high. And what we can do in this case is we use the pytest approx function here, which is what I wrote down earlier. Now, in pytest approx, what it does is that it says, okay, the result here needs to be in a range around this value with this error. And the error here is a relative error. So pytest will multiply this value with the first one, and then it expects us to be within the range of this value plus minus the product of this one with this. We can leave out the second argument, in which case we are dealing with 10 to the minus 6 as the default value. But in this case, I wanted to have a higher error. So this is now our allowed error range. So let's test that. And we see that now it tells us that all the tests run perfectly. Now, as the last part that I will show you here, I'm not going to do a complete lecture on unit tests. That would take really a little too long for such a short tutorial. But what I want to show you still is that we can actually test whether these errors here are raised correctly. For that, let me just put in this, put in this case and just let me match the error message up here. So what we have now is that we tell pytest here that it is to expect a value error, and it has to expect that the error message is what we defined here. And then we call this compute eccentricity function with an apocenter that's smaller than the pericenter. And then we can see whether or not that is true. So let me just call pytest. I didn't save that. I want to have the value error up there again. All right. So here you can see that it tells me it raised an exception, which was what I had written up here. And that's why it didn't work. But as soon as I changed it, as I actually saved that change to the value error again, now it passes and it tells me that, okay, it gets a value error here, which actually matches the right error message. If we have a different error message, then of course we expect here to get an error. It tells me that it expects it to be pericenter smaller than epicenter, but it gets that the pericenter is larger than the apocenter. We can also use some wildcards here. So now we tell our program, okay, the error message must start with epicenter and then it must say something, then apocenter, but it's not defined what belongs in between there. And if we call the program now, you also see that the test passed. This is a short introduction into what unit tests are. I really recommend you learn to use these. And there's just one part that I want to talk about at the end of this little course. So at the very end, I wanted to show you where you could get some more information about how to design your program. One source I like are the Google style guides, which you can find on Google's GitHub. And we use Python in our course, so let's just look into it. And what I like about the Google style guides is that they really don't just tell you do it this way or that way, but they always have these pros and cons sections for the different recommendations. And then they tell you what their decision is. But of course, based on the pros and cons, you might, you can make up your own mind and decide what you think is the right way to do things. Now, since we are dealing with Python, of course, I need to mention the PEP8 style guides, which are the dedicated style guides for Python, and they tell you everything from how many line breaks should be between functions and how many tabs should be at the beginning of an indent to commenting, name conventions, and so on and so forth. So you really get a very comprehensive guide of that. With this, thank you for joining me on this little course, and maybe I see you in my next video.